In this tutorial, we will be discussing enthalpy. You may remember enthalpy as H, or the change of enthalpy being delta H. This is the calorimetry at a constant pressure. These reactions are done in an aqueous solution. That's rather important because it's an aqueous solution, that means it's a solution in water. And since water is the primary solvent and there's the majority, we can actually use that as the specific heat. The pressure that we're using is typically the atmospheric pressure. Here's an example of a calorimeter. Calorimeter is often in nested foam cups, so coffee cups, containing the solution. The nesting helps to insulate it. Notice that there's also this cork lid that's on top. That also helps insulate the top of it. The glass stirrer and then the thermometer to determine the beginning and final temperatures. If we figure out the heat of the reaction, if we figure out the heat of the solution, we can figure out the heat of the reaction. And then we can break it down: the mass of the solution, the specific heat of the solution, and the change in temperature. Remember, when we're talking about solution, we're talking about it being in water, meaning that this will most likely be 4.18 times joules per grams degree Celsius. The delta H is then the exact same amount, but typically delta H is done per mole, which means we need to divide it by moles. Let's have an example. If 0.158 grams of magnesium react with 100 milliliters of solution, changes the temperature from 25.6 to 32.8. What is the delta H of the reaction per mole? Alright, so to get the delta H, we're going to need the Q first. And we know that the Q is the Cm delta T. Because this is the calorimetry and it's in a solution, I can use C being 4.18. The delta T is really easy. 32.8 minus 25.6. That comes out to be 7.2. Now the M, they give us 100 milliliters. However, typically we need to, because this is the M, we need the mass. So we're going to use the density is equal to mass over volume to figure out the actual mass. The density of water, since that is the primary solvent, is 1.00 grams per milliliter. That's going to be X over 100 milliliters, which means our mass is going to be 100.0 grams. So Q is equal to 4.18 times the mass times the change in temperature. The grams cancel and the degrees Celsius cancel, giving us 3009.6 joules. Now that's the Q of the solution. For the Q of the reaction, we're going to take the opposite of that. So that's going to be negative 3009.6. To get the delta H then, we're going to take this amount and divide it by the number of moles. Well, they give us the number of grams, so we have to convert that over to moles. So 0.158 grams of magnesium. Look on the periodic table and you find that the molar mass is 24.31 grams. Now let's take a look at the chemical reaction. The coefficient for magnesium is 1. For every 1 mole of magnesium, we have the delta H. We have the enthalpy. I'm putting that there to make sure that you realize that if there was a 2 or a 3 there, you'd have to divide it out. That comes out to be 0.00650 moles. Alright, so we have the Q and we have the moles. To find the delta H, we divide the 2. And that is equal to negative 463,015 joules per mole. Most of the time delta H is written in kilojoules because of the fact that the number is so big. So negative 463 kilojoules per mole. Let's try another example before we're done. What is the final temperature of a solution in a coffee cup calorimeter? So we're looking for the final temperature. If a 50 milliliter sample of 0.25 molar HCl is added to a 50 milliliter sample of 0.25 molar NaOH, if the initial temperature, so this is our TI, and the delta H of the reaction is negative 57.2. So they give us the delta H in the process. Delta H, we know, is equal to the Q of the reaction over the moles. So we can figure out what the Q is by looking at our materials. So we have it as 50 milliliters of a 0.25 molar solution. If we look at the reaction itself, this is the balanced chemical equation. We can determine how many moles there are that were used by looking at the molarity and the fact that the coefficient is 1. So 0.250 molar is equal to X. We need it in liters, so I'm going to divide it by 1,000. Cross multiply, and it comes out to be 0.0125 moles. Alright, so from here, the delta H is negative 57.2 kilojoules per mole, which is equal to X over 0.0125. That gives us 0.715 kilojoules for our Q. And that's the Q of the reaction. We need that in joules rather than kilojoules, so I'm going to bring it up here. 0.715 kilojoules. For every 1 kilojoule, there's 1,000 joules. So 715 joules is the Q of the reaction. We're dealing with the solution now. So the Q of the solution is going to be the opposite of that. So negative 700 to positive 715. This should be a negative number, and this should be a negative number. Alright. So now Q is equal to Cm delta T. So 715 is an aqueous solution, so we're going to use 4.18. The mass, we're talking specifically about NaOH here, because it gives us the delta H of the NaOH. 50 milliliters. Once again, it's an aqueous solution, so we're going to say that the density is 1. So 1.0 grams per milliliter is equal to X over 50 milliliters. That makes it the mass being 50 grams. And we're looking for the change in temperature. So we're going to divide that out, and we find that the change in temperature is 1.71. We know our initial temperature is 19.5, so 1.71 is equal to the final temperature minus the initial temperature, which is 19.50. We add that across, and that comes out to be 21.2 degrees Celsius. And that's how you use enthalpy in the calorimetry process.